Good evening. Welcome to CNI Seminar Series. Today we have Dr. Ranveer Chandra from Microsoft with us. We will talk on data-driven agriculture to sustainably nourish the world. Ranveer Chandra is the General Manager in M365 Copilot and the CTO of Agri-Food at Microsoft. Previously, Dr. Chandra has held various leadership roles, including the Managing Director for Research for Industry, Chief Scientist of Microsoft Azure Global, and Head of Networking Research at Microsoft Research Redmond. His research has shipped in multiple Microsoft products, including Xbox, Azure, and Windows. He is the inventor of Microsoft FarmBits, Big Data, AI, Cloud, and Edge for Agriculture, which is the Microsoft product and is being used by multiple agri-food companies. FarmBits was featured by Bill Gates on Gates Notes, and he has been invited to present the Secretary of Agriculture and on TV White Spaces for the FCC chairman. Dr. Chandra has published more than 100 papers and holds over 125 patents granted by the USPTO. He is an IEEE Fellow and ACM Fellow and has won several awards, including the MIT Technology Review's Top Innovators Under 35 and was recognized by Newsweek magazine as America's 50 most disruptive innovators 2021. Dr. Chandra has an undergraduate degree from IIT Kharagpur and India and a PhD in computer science from Cornell University. Welcome, Dr. Chandra.
Thank you. Yeah, hello everyone. I know it's late in the day and I'll stand and talk. Hopefully this will work. So yeah, it's great to be at ISC and you all do amazing work here. Today I'll talk about some of the work that I started about 10 years back. My background is in networking. I think this is the ECE department. There's a lot of networking research that happens here. I'll talk about networking, although I've done a lot of other things beyond networking now. But I also touch upon other problems which are adjacent. You can think of applications of networking. I think networking is the foundation on top of which all the other systems get built. This is a project I started 10 years back at Microsoft on agriculture and food. I was at Microsoft Research when I wrote a memo. I don't know what got into me back then. I was working from California and going to Seattle often. And then something came to me which said, I want to do this. Microsoft needs to work in this space of agriculture and food. The reason for that is, growing up, my degree, as you heard, is in computer science. It's not in agriculture. But growing up, I spent a lot of time in Bihar. That's where my grandparents used to live. So, as many of you can relate to this, in India, our parents, they would drop us. We were three brothers and a sister. They would drop us every summer at our grandparents' place and disappear for the entire summer vacation. And I wasn't looking forward to those times. I didn't like anything to do with agriculture back then because, the rest of the time I was in Jamshedpur. This is a city close to Calcutta. It has 24 hours water, 24 hours electricity. And then for 4 months every year, 3 months in the summer, 1 month in the winter, I was spending time in those villages in Bihar, close to Bhagalpur. It was quite a trek to get there. From Jamshedpur, I would have to take 2 trains to get to Munger, then take a bus to get to Bhagalpur, take another bus to get to Amarpur, take an auto rickshaw, and then the final lap was the final leg used to be we had to take a tum-tum, horse cart, and invariably we used to have to cross this bridge, which used to be called the Tuti Bridge. It was across a river; it would always be broken because every floods it would get damaged, and we had to cross that. And these villages, the reason I didn't enjoy the summer and winter vacations that much is because these villages, they did not have any electricity, no toilets. There was nothing to do there. But that said, I did see extreme forms of poverty there in those villages. The one image that had struck my mind, which drove me to this particular project, was my mom would do the puja and she would keep the offerings outside the house, and there was a swarm of kids that were there just to grab something to eat. This was back in the 80s and early 90s, and that's the image that has struck to me. So even though I did computer science, as it happens, if you're top of the class, you go do a PhD. It just followed everything. But then after that, this is one thing which I was like, I want to give back with all the work we're doing. That's what led to the start of the project. But our mission through all of this is actually much more. So I know you all are coming from an electrical engineering, computer science background. You might not be as much aware. Yeah. Oh, I see. Yeah. Oh, okay. This works? Yeah. This will automatically disappear, I guess, right?
Yes. Thanks. If you click on this more.
Yeah. Hide.
Right.
Okay. Yeah. So as I said, the what we were after is a much bigger problem. So I'll just tell you a little bit about the world's food problem. The world needs around 50% more food compared to today's levels to feed the growing population of the world. And it is not just about growing more food, it's about growing good, nutritious food. And we have to grow this food even though the amount of arable land is not increasing. The water levels are receding, there is climate change, the soils are not getting any richer. So the key question then is, how do you get to this increased good food production to feed the growing population of the world? So towards this goal, at one of the questions would be, okay, what is Microsoft's play in it? What's the role that we as technologists can play? So our vision is that of one of the key enablers we think that can help us get to this increased sustainable good food production is that of a data-driven agri-food system. What we mean by data-driven agri-food system is if every entity in the agriculture and food supply chain, all the way from input companies, seed companies to equipment companies, ag retailers, the farmer, the cooperatives, food processors, distributors, supply chain, if every entity in the food supply chain started to use data and AI, it leads to increased efficiencies throughout the supply chain. Every entity, you'll start seeing significant improvements. But it doesn't just stop there. If you could connect the entire food supply chain, that is, if you could share data across the entire food supply chain, this leads to new efficiencies. This leads to new business models. So over the last 10 years at Microsoft, we have been working on different aspects of this connected food supply chain, all the way from making your farms more data-driven. How do you enable farmers to start using data and AI? I'll focus most of the talk on this. But the other parts that we are doing, which I won't talk much about, so feel free to ask questions. One is on the food supply chain. That is, the question we are asking is, how do you make the food supply chain more connected? How do you carry information all the way from the farm to the fork, to the consumer? If for whatever food you're eating, if you're able to tell which farm it came from, did it use child labor, how much water did they use? So, one of the things when I tell people this problem, the first thing they say is, well, blockchain solves the problem. Well, blockchain only solves part of the problem. The bigger problem is, what do you put in the blockchain? So a lot of our innovations have been on hands-free digitization of the food supply chain. That is, can you, in a hands-free way, figure out what is that data that you need to put in the blockchain? And the other piece that we are also looking at here is trying to model the entire food supply chain as a knowledge graph. That is, what if I ask you the question, if there is a drought in Chile, how is that going to impact, say, the price of wheat in Bangalore? Now, to answer these questions, you have to look at the entire supply chain, and we model that as a knowledge graph so that you can start reasoning over it. The third thing we are looking at is more downstream on using AI to accelerate the invention of new ingredients. That is, what does it take to come up with a new ingredient that has that perfect taste, that perfect flavor, that perfect smell, that perfect nutrition? And in order to do that, using artificial intelligence to come up with it, to speed up the entire pipeline, to like these new molecules. In the rest of the talk, I'm going to mostly focus on the agriculture side of things. So the first thing I wanted to talk about with agriculture is the relationship between agriculture and climate change. That is, agriculture is one of the biggest emitters of greenhouse gases. That the fertilizer that people put in the farm, the fertilizer, excess nitrogen that you put, goes up in the form of nitrous oxide. And that's one of the most potent greenhouse gases. Agriculture is not just one of the biggest emitters, and that's just, nitrogen is just one. There is cows, methane emissions, and so on. So that's one of the biggest emitters of greenhouse gases. Agriculture is not just one of the biggest emitters of greenhouse gases, it's one of the most impacted by climate change. Farmers are the ones who rely a lot on weather, on predictability in weather, and they are the most impacted with climate change. And not just that, agriculture, if done right, can actually be a solution to climate change. Plants, because of photosynthesis, they take carbon from the air and they can put that carbon back in soil. So if you practice the right agricultural practices, this carbon can be taken back from the atmosphere and put back in the soil. So towards this vision, one of the things that we have been looking at for the last 10 years is this concept of data-driven agriculture. One of the things that data-driven agriculture could enable is you can map every farm in the world with data. For example, imagine I took you to a farm and I asked you the question, what is the soil moisture level 6 inches below the soil surface throughout the farm? So in order to build these maps with data, if you could build these kind of maps for water, for nitrogen, for phosphorus, for potassium, for all of these carbon, you can then start enabling techniques like precision agriculture. This might have been a term many of you might have heard. Precision agriculture refers to site-specific application of input. So given a farm, you should apply water where it is needed, pesticide where it is needed, nutrients where it is needed. Typically, most farmers, what they do is they'll take water and spray it uniformly throughout the farm. Take nitrogen, put it uniformly throughout the farm. If you had a map like this, you could do site-specific application of inputs. And precision agriculture has been shown to, one, improve yields. You can take care of plants better, you grow more, you're able to increase yields. You're able to reduce cost. You use less water, less chemicals. If you do this, it's also better for the environment for the same reasons. You're not putting in more chemicals than are needed. You're not wasting water. And this is precision agriculture. The other thing is regenerative agriculture is another term that is there in the agriculture community. That is, can the farmers use less chemicals? Can they farm in a particular way so that there's more carbon that is sequestered in the soil? Can you increase the soil organic matter of carbon? The thing is, precision agriculture as a term, we didn't coin it. It was invented back in the 80s. Yet its adoption worldwide is significantly limited. And the biggest reason this adoption is limited is the cost of these data-driven agriculture solutions. When I started the project, I had actually visited UC Davis, University of California, Davis, which has a very good agriculture school. They had an expo going on. There were several companies that were presenting the latest ag-related equipment. And the cheapest package, a sensor package of 5 sensors, was for $8,000 and a recurring cost. For most farmers, why would they buy 5 sensors? What's the ROI if I just put 5 sensors, and that too for $8,000? They're not making that much money. And in fact, there was a recent study by McKinsey in 2022 where it looked at things like the major barrier to adoption of these digital technologies is high cost of these solutions. Any digital agriculture solution is just super high cost, and that makes the ROI very unclear. What's the return of investment if I buy these sensors? So that became our mission. So the mission that we were after was, can you make these digital agriculture solutions more affordable? Can you enable any farmer anywhere in the world to start using data and AI? So when I started this project in 2014, but from 2010 onwards, I was actually going and volunteering in farms in the US. And that led me to interesting insights about farmers. Farmers, they work a lot. Their day starts before dawn and ends after dusk. They're spending a lot of time in the field. The other realization was that these farmers, they know a lot about their farm. There was one farmer close to Microsoft campus. We have a demo farm there. This farmer could feel the soil and say what's going on. There was another farmer I worked with in upstate New York. He would taste the soil and say what's going on. They know a lot about the farm. So our vision when we were talking about data and AI-driven agriculture was not to replace a farmer. They know a lot about the farm, but our goal was to augment a farmer's knowledge with data and AI. Can you supplement them with data and AI so that a lot of the work that they were doing with guesswork, can you replace guesswork with data and AI? So then we started looking at, okay, what are the key challenges in enabling data and data-driven agriculture? And the first challenge, which many of you could relate to, is that of connectivity in the middle of a farm. One of the challenges was the farmer's house. This is in the US, and even over here, there's some challenges. But the farmer's house might have some sort of connectivity to the cloud, but the actual farm is a few miles away. Sometimes when the farmer plants the seeds, there's connectivity. By the time the crops grow, the connectivity is gone. So the question then was, how do you bring data from the middle of the farm to the farmer's house? And this was in the US, for example, there was a study by the USDA which said 60% of farmland in the US has very weak internet connectivity. Even over here, people say connectivity is a solved problem. It really is not. If you start going to the farms and such, you start running into issues of connectivity. So then the question was, how do you bring all of this data back to the farmer's house? One of the things that I started working on initially when I joined Microsoft is a solution around TV white spaces. So we looked at, can you use unused TV channels to send and receive data? The key idea was to use these Wi-Fi, like a Wi-Fi router, and send the Wi-Fi signals in empty TV channels. This is, TV you watch using antennas. Many of you are young, you might not remember, but that TV that people watch with antennas. And the key idea was, when you browse through TV channels, sometimes on some TV channels you get a reception. On the other channels, all you see is white noise, nothing coming there. The key idea was, can you put these Wi-Fi signals in those noisy TV channels in a way that doesn't interfere with your TV reception in an adjacent channel? So you could be watching channel 7 at home, on channel 8 we could be sending Wi-Fi signals. And the reason this is so cool is, compared to Wi-Fi at the same power level, in UHF TV channels, your signals go 4 times farther. In VHF, they go 12 times farther. And this is in free space. Once you put in crops, trees, canopies, your signals just keep going through. And the interesting thing about agriculture is that, TV towers are where people are. You have TV towers in cities. The farms are away from the cities. So in the middle of a farm, most of the channels are just white noise. I was actually giving this talk at the National Corn Growers Association in the US. And there I was talking about, I was saying, imagine if even like there are 20 TV channels that are used. There are 50 TV channels worldwide. The spectrum is occupied by TV channels. So there was a lady farmer from Kansas. She raised her hand. She said, in my farmhouse, I only get 2 TV channels. The rest is just empty. The more empty channels there are, the more capacity there is. Each TV channel in the US is 6 megahertz wide. In India and in other places, it's 8 megahertz wide. If I have 50 TV channels, even if I have 20 TV channels, you're talking of over 100 megahertz of unused spectrum in the middle of the farm. So this was the thing that we built back then. We worked with the FCC a couple years back. The FCC actually made use of this technology legal in the middle of farms. And we've written multiple papers and so on this particular technology. But over the years, we started looking at other ways as well. Like, by the way, with this technology, we've connected palm plantations in Malaysia. We've used this in multiple places around the world. But then we've also started looking at other technologies. One of the things we're looking at is, can you enable private 5G in the middle of a farm? So for example, can you, again, either using this spectrum or another spectrum, can a farmer on top of their house or a grain silo mount an antenna and connect the entire farm? The other thing, very recently, we published quite a few papers on this, on another concept of using satellite IoT devices. In fact, just in November at ACM Mobicom, we had a paper on this as well, which won one of the awards at ACM Mobicom. The idea there is these sensors that you have here, what if you could directly talk to satellite instead of talking to a gateway? Because one of the key challenges with a lot of these Internet of Things devices is you have to set up the device, you also have to set up the gateway. Right? All these devices talk to the gateway. If you were directly talking to satellite, you don't need any of these gateways. With these satellites, you're not looking at like the Starlink satellites. You're looking at really small satellites, like big. It's like a picosat, and they are very small. They have interesting challenges that come up. And the key idea is then, if you deploy a sensor, can I just put the sensor with the antenna mounted up? Can you then use it to send data from anywhere on the planet? And this could be really low cost. We've actually launched 6 satellites that are orbiting the Earth to start collecting this type of data. But that again requires a lot of new innovation. Some of the things we've looked at is, some of the standard networking problems around medium access control, because they're interesting challenges. These satellites are moving all around the Earth. You have multiple devices, and these devices, if they start sending data simultaneously to the satellite, will start causing collisions. So how do you make sure that all of them can start communicating at the same time? And there's some very interesting problems in that space. I can go deeper into that. These are like, each one of them is a separate paper, half an hour talk in its own self, but I'm happy to get into details because you're a networking audience. By the way, feel free to ask questions in the middle of the talk if there are any. So the second challenge we had to address first is, but the key takeaway from the previous part I was talking about is, when we talk of data-driven agriculture, it's critical to address the connectivity problem in the middle of a farm. If the farms are not connected, you're not going to enable data-driven agriculture. All these things about generative AI and everything else, the fundamental assumption is that your farms are connected. The second thing we had to address was, we had to build maps like this. Suppose the previous question I told you, if I took you to a farm, like even outside here, to one of the lawns, and I said, what is the soil moisture level? 6 inches below the surface throughout the farm. If you ask a soil scientist, they'll say, well, you need to deploy a sensor every 10 meters. But deploying a sensor every 10 meters is expensive to deploy, to manage. It will come in the way of the farmer as the farmer does the day-to-day job. So the key question we asked was this: can we build a map like that using very few sensors? And towards that, our key insight was to use AI. So the way we go about building these maps is, first, for any farm, we collect aerial imagery. This could be either you fly a drone and you collect an aerial imagery of a farm. We built a lot of work. We've done a lot of work on the drone ecosystem as well. If you don't have drones, there was another hacky project we did. Actually, we deployed it here as well in GKVK, the Agriculture Institute here. The key idea there was to use a helium-filled balloon. This is like 4 to 6 feet in diameter. The key thing we built was a weatherproof mount where a farmer could put their smartphone with the camera facing down and a battery pack attached to it And this is 150 to 200 feet above the surface. And using that, you can start taking images of your farm. In fact, in places like India or sub-Saharan Africa, where labor is inexpensive, someone could just walk around with the balloon, and then you can use computer vision techniques and AI techniques to stabilize the imagery to build maps like this. In fact, one of the key challenges that we had to address is in a drone, your camera is stable. They have a lot of work done on stabilizing the camera. But in the case of a balloon, it moves around with wind. It's not always facing down. So we had to come up with innovative techniques to stabilize it. So Bill Gates covered our stuff in Gates Notes. If you see his video, he's in a farm where we are taking him around and he's actually walking with a balloon. He came up with an interesting idea. He was like, hey, how will you get helium in the middle of a farm? Now, that's, again, a challenge that we have to address. His idea was, well, in the middle of a farm, you might have a lot of methane, and to use methane in these balloons. The challenge with methane, though, is it's inflammable. So we have to be careful if we have to use methane in the middle of a farm. But in most places, if you don't have drones or balloons, we end up using satellite imaging. Most places, this is what we use to get this kind of a view of the farm. Once we have this, we figure out what are the right places using AI to sample the farm, either using sensors or just taking samples for getting lab data. We then use that to, we then build ML models. This is using Bayesian models. Essentially what it is wherever you have the sensor reading and you have the aerial imagery, you use that to train the model, and then you use that trained model to predict these values in other parts of the farm. So we've done this. So the state of the art before this technique used to be that of method called Craiging's method. I don't know how many of you know Craiging's method. It's essentially a Gaussian method. It says if this is A, this is B. Everything in between is between A and B, kind of. You assume a Gaussian distribution, use that to interpolate. And that's known to be very, very inaccurate. The key thing here is rather than just using that, if you include aerial imagery on top of it, it significantly increases the accuracy of these measurements. So we wrote a paper where we showed that for soil moisture, soil temperature, and soil pH, using this multimodal technique gives you 3 times more accurate maps for those 3 parameters. In fact, now we build this for soil nitrogen, soil carbon, and many other parameters as well. One of the things, this was done by my student back in the day, another multimodal AI technique. He's this guy, he was a PhD student at MIT. Now he's a professor at UPenn. Mingmin, he did this work called SpaceEye. The challenge that we were looking at was, if you look at satellite imagery, more than 70% of satellite imagery is cloudy. All you see is this. What we wanted was a way to see through the satellite imagery, through the clouds and satellite imagery. So the way we solved this problem was we looked at, again, multimodal. We looked at the optical satellites, and we also looked at SAR satellites, synthetic aperture radar. And using SAR, radar signals, they go through the clouds and they reflect differently from different surfaces. And we use that along with optical to start predicting what's happening below the clouds in satellite imagery. You can see, even though this is cloudy, you can tell when a farm was tilled, when a farm was, when did emergence happen, when was irrigation done, all of that, even though the satellite imagery is cloudy. In fact, for 3 of the 4 seasons, our accuracy of predicting below the clouds was over 95%. The challenge came when it is snow. With snow and clouds, it becomes a bit tricky. So what we've done as a result of this is we've released a lot of these. As of a few months back, we've released the entire source code around multimodal AI in open source. It's called farmvibes.ai, including the TV whitespaces piece, by the way, the layout, the die, the chip, the Mac, all of that is open source right now, along with all the AI workflows that you're seeing here. If you go to GitHub and the farmvibes.ai, you'll find this open source. Would love for you all to try it. It has some of the SAR data as well. And the key takeaway for us in all of this work, since we started working on AI, was most of the AI work in agriculture with remote sensing was only looking at one modality, just looking at satellite imagery or drone imagery. The key takeaway for us is you need to look at multiple modalities together, this multimodal AI, and that leads to new insights. Like, for example, I talked about using sensor data plus aerial imagery to build those maps, using SAR plus optical imagery to see through the clouds and satellite imagery. Similarly, we have many of these multimodal techniques. Things like, if I have a drone that you fly periodically that takes very high resolution imagery, and then you have a satellite that on a daily basis is giving you coarse-grained imagery of the farm. Can you combine these to come up with very high resolution imagery of the farm? High resolution imagery is important, for example, if you want to see pests or diseases and so on. So as I said, we've open sourced this entire thing. Would love for you all to try it out and use it in hackathon. It's all under the MIT license, so it's not like we are making any money. In fact, we've Right now in Baramati, we've used this to set up. Baramati is in Pune, close to Pune. There's a village called Baramati where we've set up a farm of the future. You'll hear more about it soon. And there we've shown how you could improve the productivity of sugarcane, of different vegetables, tomatoes using AI. And in fact, we're using that same thing in a million farmer project in Uttar Pradesh with the World Bank and the UP government to get the farmers to adopt low carbon rice. All of that building on top of this particular technology that I'm talking about here. The third challenge that we had to address to make the entire thing affordable is again a systems problem. I talked about how you can bring a lot of data from the middle of the farm to the farmer's house, but the connectivity from the farmer's house to the cloud is weak. Like many farmers, they pay for broadband, but all they get is 1 to 3 megabits of second connectivity to the cloud. Even over here, like even in Bangalore, when I was coming here, I'm staying at ITC Gardenia. From there to here, there were portions where I didn't get good internet connectivity. Now, the thing is, in a 15-minute drone flight, you could be getting several gigabytes of data. If I don't have really high bandwidth connectivity to the cloud, how will you bring the benefits of all of this AI and computer vision to the farmer? So our key insight was that most farmers, they have a PC like this one. If they don't have a PC, we would ship them a PC form factor device. And then everything you're seeing in this big gray box runs on the PC. You get data from sensors, from drones, you do this orthomosaicing, a 3D point cloud, you generate these heat maps. The last column is something we don't do. We are not the experts at Microsoft in agriculture. We work with partners who can build these applications. But this is all running locally in the farm. We also have data. We get data from cameras. We do small language models on the edge as well. And all of this data is lazily synced with the cloud. And we also have a web server. In case you lose internet access, you could then still access all the data that's sitting here. So, we've deployed this in multiple farms around the world at this point in the US, in India, in Africa, and Australia, and so on. And some of the ways in which the farmers are using it, just to see what are the benefits that farmers are getting. This is one of the things which we have is microclimate forecasting. That is, the weather in the middle of a farm could be very different from the weather at the weather station. Like in this case, this is a testimonial by the farmer. This is a 8,000 acre farm in Eastern Washington. There was a particular part of the farm that was infested with weeds. The farmer he wanted to spray herbicide to kill the weeds. He looked at the weather forecast. The weather forecast said it was going to be 42 degrees Fahrenheit, which is above freezing. We said it was going to be 31 degrees Fahrenheit, below freezing. It was actually 30. It was good he didn't spray chemicals, otherwise he would have lost his crop. And the way we built this microclimate prediction was again using multimodal AI. That is, if you have a sensor in the farm and you have the weather station predictions, we combine those to start making very hyperlocal predictions in the middle of a farm. This is another use case. This is in upstate New York. This is a 4-kilometer stretch. The farmer wanted to know how his cows were doing in the middle of the pasture when they're out in pasture. So we flew the drone, we transmitted the data over the TV white spaces to an edge device in the middle of the farm in the farmer's office. And within 30 minutes, we could flag things like from left to right, the grass is growing well, there is a water puddle that needs to be fixed before the next planting season. The cows are pooping well, which is also important information for the farmer. This is deep learning on cow poop. This is where the cows are. This is a stray cow that needs to be herded in. All of this within 30 minutes of flying the drone. This is a farm close to Microsoft campus where we do a lot of demos. We show the farmer these beautiful pictures and we overlay it with data. For example, we are able to flag that this part of the farm is still moist, even though we did not have a sensor over there. This was after the farmer had applied lime. We were able to flag that these parts of the farm are still acidic. The farmer needs to reapply lime before planting the seeds. This is, again, using all the things I talked about, from connectivity to multimodal AI to actually building a service that can be used by the farmers. This is in upstate New York, where we put these cameras on multiple cow sheds. We are seeing how the cows are moving, whether a cow is sick, and so on. This is like a baby monitor for cows, right, to see how the cows are doing. So then one of the questions we asked, there was one of the farmers that we've been working with him for 6 years. You'll see a video of him later in this presentation. And we asked him, how has all this data and AI helped him over the last 6 years? So he walked us through his entire crop life cycle, all the way from pre-planting, this is before he's planted, to when he's planting, to post-planting, all the decisions he has to make and all the tech he had to use. After the crop has emerged, it has come out, the different actions he needs to take, the harvesting, and post-harvest as well, all the different things he needs to do, and all the technologies that he's been using: connectivity, Power BI, IoT, and so on. And this is some of the impact that he's seen, this particular farmer. For one particular chemical, he was able to save more than 38% of the chemicals that we use. This was a six-figure number. This is the amount of grain utilization in storage. A particular part of the farm, he could double the yield based on the recommendations that we were providing. So these are just some of the ways in which data and AI is helping farmers in different parts of the world. One of the things we've also done is, in addition to just advancing the science and shipping products, we are also looking at how do you benefit society with all of this, all of these technologies. One of the things we built was a FarmBeat student kit. So this was the project that we had, where we built a student kit and a curriculum around it. So there was a hackathon at Microsoft campus where we brought many teachers from high schools across America. And these are high schools, rural high schools, in the where the farmers' kids go. And we got them over to Microsoft campus. We had a hackathon to come up with a curriculum that could be used in high schools across America. The reason we did this was to bridge the skilling gap. In the US, we need more and more people with the data and AI talent. And in rural communities, they don't have that data and AI skill. So with this, you could get the farmers to get more equipped, more skilled in data and AI. In fact, there was my personal motivation in doing this particular kit was to make agriculture cool again. One of the challenges with agriculture is that most of the farmers, there is a problem in the US and worldwide that there is an aging population of farmers. That is, the next generation of farmers don't want to do farming. It's happening in the US, it's happening here. Like, my grandparents were farmers, I'm not farming. And even over here, the farm that I talked about, where I grew up, many of my friends who were farmers' kids, they'll go to Delhi, they'll pull a rickshaw, work in a restaurant, but they don't want to farm. My hope is, if you can show how cool agriculture can be with all this tech, more and more farmers will go back to agriculture. Like the farmer, I'll show his video in the end. He's a fifth-generation wheat farmer. He went to University of Washington, studied computer science, but with all the tech, he decided to go back and get back into farming. The hope is this will encourage more and more people to go back. The other thing we are continuing to work on is, we are still far from the vision that I talked about. The vision, this is a passion of ours, is how do you democratize AI-driven agriculture? How do you get every farmer around the world to start using data and AI? We are still far from it. I think we've just scratched the surface in what's possible with data and AI. One of the challenges in democratizing AI-driven agriculture is the cost of these IoT solutions. That I talked about different ways of reducing cost, but the cost of each sensor is still quite a bit. If you want an industrial grade sensor for electrical conductivity sensing in the farm, that sensor is over $1,000. Most farmers in the US, of course, they'll hesitate. In like low income countries, like in emerging markets, like farmers, they won't spend $1,000 to deploy a sensor in the farm. Yet, many of the farmers, these smallholder farmers worldwide, there are over 500 million smallholder farmers worldwide. Many of them have a smartphone. So the key insight we had, and you all will appreciate it as networking experts, is the key insight we had is that if the farmer has a smartphone, even if it is an inexpensive Android phone, it has a Wi-Fi chipset. If it has a Wi-Fi chipset, the key idea was, can you measure the time of flight of the Wi-Fi signal? The time of flight of the Wi-Fi signal, like from here below the soil to get to another point, if you can measure that time of flight depends on the permittivity of the material. So if the soil is wet, it will take longer to traverse the same distance. But the challenge is this time is of the order of nanoseconds. It's really hard to measure. So this was actually done with by my student. She's now at Yale. And then the key insight we had was that most of these chipsets have multiple antennas. If they have multiple antennas, then rather than measuring the absolute time of flight, you could measure the relative time of flight between the antennas. And that became a tractable problem. We actually solved it, built it. We showed it to Bill when Bill Gates came to the farm. And the title of Bill Gates' blog then was, "Can the Wi-Fi in your phone help feed the world?" Because the vision then is, anyone could just take their phone close to soil and start getting these measurements. That's the vision with which we are building this. So when we did this got an award at the ACM Mobicom again. And I was actually at the National Academies in the US in 2020, just before COVID hit. That was my last trip. I was giving this talk at the National Academies, and one of the people in the audience was Professor Ratanlal. Professor Ratanlal won the World Food Prize in Ohio State, and he won the World Food Prize in 2020. That's equivalent to the Nobel Prize in Agriculture. And Professor Lal was like, hey, if you all can measure soil moisture and EC, I can use it to measure soil carbon. So soil carbon, by the way, is a very, very important measure for different things. If you can measure soil organic carbon, it tells you how healthy the soil is. The more the soil organic carbon, it can retain water, it's better for the environment and so on. So then what we did is we sponsored a postdoc at Ohio State. And over the years, just in November, again, we had a paper that we published where we showed how you could use a phone where it's not just the electromagnetic signal, but along with the camera, if you combine these, you can start making accurate predictions for soil organic carbon, which we believe is a big disruption. So now that student of mine, Jiang, she's doing a startup around this. We're trying to democratize sensing of soil. But that's the vision, that anyone with a smartphone should be able to measure soil quality. Now, just switching gears a little bit, I've been working for some time. I talked about what we built first was a data platform. Then we looked at traditional AI, is what I'll call it, and then ChatGPT happened. And then one of the questions we asked is, ChatGPT with all the copilots, how will this transform agriculture? So we different stakeholders, different personas in the agriculture and food value chain. And we looked at what is the impact that copilots are going to have, from a farmer to an agronomist to a policymaker, a banker, and so on. So one of the first things we went about doing, this was about 1.5 years back, we said, okay, for entire Washington state, let's try to build a copilot for every farm in Washington state. So what we did was, we did the first thing, which was, so this is a product from Microsoft, Azure Data Manager for Agriculture. This is using the initial Palm Beach research we did, it became a product. What this does is, for any polygon, a polygon could be a farm, a field, a plot. For that polygon, it will bring together all the data for that polygon in one place, from sensors, satellites, drones, weather stations, tractors, and so on, everything in one place. So every farm would be a new polygon. And then it is all stored in a common data model. This is critical because then this enables the use of AI on top of it. Once you do that, then on a daily basis, we run farmvibes.ai. This is the multimodal AI I talked about. That is, you run it on a daily basis. We also have a partnership with Bayer. So Bayer's building ag-powered services on top of the Azure Data Manager for Agriculture. And using that, what we create is what we call a farm context. That is, for any polygon in Washington state, any farm, we would have the context of the farm. The context is things like, this farmer planted this seed variety on this date, they irrigated on this date, and so on. Everything is stored in the farm context. So when a farmer asks a question, say the question could be, what should I be applying in my farm tomorrow? We take that prompt, and to that prompt, we add additional information, like, this is a farmer in Eastern Washington, he's planted wheat, this is the date in which emergence happened, this chemical has been applied. And to that farm context, we also add additional knowledge from the USDA. We then push all of this to Azure OpenAI and come back with a response. This is the kind of responses we get from our Copilot for any farm in Washington state. You could say things like, what's the health and vigor of my crop? What does the NDVI values mean? What have I applied in the farm? You can ask about, show me how my farm has been doing, plot it in a graph, and so on. This was actually 25 questions that were given by a smallholder farmer near Microsoft campus. And he wanted to see how well a Copilot would do on his questions. And for 21 of the 25 questions, he gave our answers 5 out of 5. For the remaining 4, he gave it a 3 out of 4. The other thing that this is able to do, it's also able to answer budget-related questions. A farmer is essentially a business. A farmer asks a question, what should I, if I applied this chemical, how will it impact my profit and loss? And this is the kind of results that this is able to give. Then in 2023, I was actually attending World Agri-Tech. This is one of the biggest agriculture conferences in the world. And one of the venture capitalists, he came to me and said, hey, can AI pass the agronomist exam? So in the US, if someone has to be an agronomist, they want to call themselves an agronomist, they need to pass this exam. It's a certified crop advisor exam. So we then took GPT-4 and we did include, like, we tried different techniques like ensemble and things like that. And GPT-4 got quite good answers in this particular exam. We did this for Embrapa in Brazil, for agronomists as well, and we got 84% grades. In India, we took the agri exam and we got 79% grades, which was more than the #1 human that took the exam. This is an AI agronomist. Then I asked the question to that venture capitalist as to, why did you ask us to do this? His point was, right now, farmers are confused when they, if they see a problem, they'll ask an agronomist. Every agronomist will tell them a different answer about what they should be doing. So they're often confused as to what they should be doing. This AI could be a very powerful second opinion for farmers. So I actually put this on LinkedIn as well. We wrote a paper on it. I put it on LinkedIn, and I got two sets of responses. One set of responses I got was from the agronomists themselves. They're like, passing an exam doesn't mean you can be an agronomist. So I was like, yeah, we're not saying you replace an agronomist, but this could be a very powerful agronomist assistant. But the other set of responses, which got the most likes and comments, most likely came from farmers. They were like, we don't get like authoritative responses from the agronomists that we work with. So this then, we believe, can be one of the disruptions in agriculture. Imagine every farmer equipped with an AI agronomist tool, an assistant that they can then consult with, or every agronomist can then talk to this particular tool and get responses. The thing is, with AI, one thing that we have to be careful about is it still makes mistakes. Like in the agri exam, this was one of the questions. Who's the advocate of the Marthandam Rural Development Program? GPT-4 did not know the answer, but it made an intelligent guess. It said, this is an India exam from India, so must be an Indian. It's Mahatma Gandhi. Well, the answer wasn't Mahatma Gandhi, it was Spencer Hatch. So this is when we are like, GPT-4 by itself is good, but then the question we asked was, what does it take to build an agriculture-specific model? So we went about, and the reason this was important is, for example, if you ask the question, what is the best time to plant trees and shrubs? Depending on which state you're in, the answer could be different. But this is old at this time, but most of these models will just come up with a standard answer. So then one of the things we looked at was, what does it take to customize these large models? Take a large model and GPT-4, and we were the first to fine-tune GPT-4 for any industry, and in this case, it was for agriculture. So we took the data set from USDA, from Brazilian Embrapa, and from India. We built an entire pipeline for fine-tuning GPT-4 around QA generation fine-tuning, and we built these fine-tuning pipelines, and we compared it with another approach, the RAG approach. I don't know how familiar you all are with RAG and fine-tuning. RAG stands for Retrieval Augmented Generation. That is, if I give a prompt, if I have a huge database, I'll take the relevant data and augment the prompt and ask the big model to answer the question. With fine-tuning, I'm embedding that data in the model itself. And we compared both RAG and fine-tuning and RAG plus fine-tuning to see how well it performed. I won't go into the details, but the key takeaway that we had, that I got really excited with the results, was, if all you're looking at is accuracy, RAG and fine-tuning are mostly similar. Fine-tuning gave us 6% improvement in the results. But the part that I was really excited about is, especially if you're looking at new knowledge, like, the kind of scenarios. Imagine a farmer in India asks a question, I'm seeing these brown spots on leaves, what's the problem? Imagine a large model that says, I don't know the answer based on the data I have, but your growing conditions are very similar to the growing conditions in Brazil, based on which this is what we should be doing. And that's what we found, that fine-tuning showed these emergent properties of learning these kind of relationships across different documents. And that's something which we actually, in the paper, if you see this paper, you'll find a systematic study where what we did was we looked at across all the 50 states in the US. We looked at questions that were common in 3+ states. We kept the answers for 3 of the states and removed it from all the other states. And we used that to train the model. And we saw a significant improvement of 25 percentage points when we fine-tuned the model. And this is something that we are pursuing, like we're continuously making this approach even better. One of the other things which we started looking at was multimodal GPT and its responses, its application in agriculture. There are a lot of apps in the App Store where you take a picture of a leaf, take a picture of a flower, it'll tell you what it is. Here with these large language models, it not only tells you what it is, it also tells you why it thinks what it is. Like in this case, the question, this was data from the Ministry of Agriculture in India. The question was, what is this worm? I'm a cotton farm in India. It says this is a cotton bollworm, and it tells you why it thinks so. In this case, if you ask the question, the same question, even though this is so tiny, it then first says, I cannot, without a clearer image, I'm not very confident on what it is, but based on the location and where it is, it's probably a caterpillar of a cotton bollworm. This was an interesting use case again. The question was, I'm a chili farmer in India. I'm seeing this disease in the roots. What is it? It said, it seems like a root knot nematode. Then I asked the question, are you sure it's not root rot? Because I got these labeled images from an agronomist in India. They said it's root rot. It said, it could be root rot, but based on the presence of galls and the roots is a characteristic symptom of root knot nematode. Then we sent it back to the agronomist here, and they said, yeah, your AI was right. Our agronomist actually made a mistake. This is a friend of mine who's here in Bangalore. He heads our Azure AI team here. He has a farm, and he asked this question. I'm a farmer from India, Karnataka, Vijaypura district. I planted Baidagi chilies. It's super late rainfall this year. It's been irrigated using sprinklers. I'm seeing small holes on leaves. What is wrong with my plant, and what could be causing it? Just based on this image, GPT-4 came up with a very generic answer. It's all possible use cases. Then you give it another image, and then it just says, okay, based on this image, it seems it's bacterial leaf spot. You can then give it another close-up. It says, yep, this confirms the presence of bacterial leaf spot in these plants. You can then ask, for example, Bing or Google or something else, or an authoritative data set as to what should I do to fix this particular disease. So multimodal AI and multimodal AI, even the context of LLMs and transformer models, we believe is a significant disruption in this entire field. And then the new thing, this is around reasoning. I don't know how many of you following O1 and O3 models that have come out from OpenAI. They are pretty disruptive. Like, this was a talk I was giving at a keynote I gave at the Agriculture Retailers Conference. This is like a big event in the US, where all the ag retailers, the people who sell inputs to farmers, it's their event. And there I was showing them one example where reasoning could help. For example, the question could be, I'm an ag retailer, I have 3 warehouses, 5 farming regions, each warehouse has limited stock of NPK, these are the 3 fertilizers, and this is the warehouses, how should I distribute it? So this is the problem. I have to determine the optimal allocation of fertilizers to regions, each warehouse fertilizer cannot be exceeded. I give the constraints as well. And then these reasoning models can now go and figure out what you want from this problem, formulate the problem, and come up with the answer. Like, it goes on thinking, it'll come up with formulating, mapping the linear program. It then goes about thinking further, trying to do an allocation, finalizing the allocations. It then tries to come with it. It comes reevaluating this. So this is the entire chain of thought that reasoning model is doing and wrapping up allocations. And after this, I stopped taking screenshots. But finally, it thought for over 90 seconds and came back with a response about what the farmer should be doing, or what, in this case, the ag retailer should be doing. We believe this is going to be the next big disruption in AI for agriculture, and just broadly in AI. And the last point I wanted to touch upon when we think of all the different use cases around and all the innovations that are happening in AI is around small language models and how small language models could interact with large language models. One of the scenarios we were looking at here was a farmer in a tractor trying to ask a question, and the tractor is not always connected to the internet. How do you get the benefits of these SLMs and LLMs to the farmers? So our architecture here is the following. In the cloud, we have like a huge model, which is fine-tuned GPT-4 or something like that. We have a suite of small models, like, these are SLMs that could run on the edge itself. We call them small language models, but there's still a few billion parameters. And these could be per crop or per state and so on. And then on a daily basis, what we do is for every farm, we would run the farm context that I showed in the earlier slide. And we store it in a context manager. Then on the edge, on a daily basis, what we'll do is we'll store the context on the edge. So when someone asks a question, we do the speech to text, we'll do the orchestration, we'll figure out which LM to use, we'll use a RAG, figure out the right model selection. When the answer comes, we'll do the text back to speech and return back the answer to the farmer. This is the vision that we have of any industry. I talk about agriculture, but it's the same for healthcare, for any industry that you think of. It's not going to be just one model. It's going to be a suite of models, and you'll have to orchestrate across all of these models to come up with the right answer. And this, again, it's part of it is an AI problem. A huge part is an AI problem, but a huge part of it is also a systems and networking problem as well. How do you run what, where, deliver the right value to the end customer? So I wanted to end by showing you this video from the farmer. I think I might have to increase the volume here, right? I'll just try. Let's see if this works. Farmer in Eastern Washington State. I want to show you things that first one is our state's IoT. As you can see, it is a sensor that is connected up to the ground and sending those results all the way up to space that they recorded
That soil moisture sensor is actually going to be increasing since we got a much needed rain yesterday. Throughout the past 6 years, we have been working with Microsoft on technology throughout the farm. And one of the other things that I want to show you is the Farm Vibes chatbot. This chatbot is disconnected, doesn't need any internet, which is great because even though I do sometimes have cell service, I usually have no actual cell data. And we have one Starlink that's rolled out onto all of our tractors and sprayers and combines. It's very cost effective. So here's my chatbot. It has all of my manuals in it. And I'm going to ask it a question. How much hydraulic oil does it take to fill a 9R John Deere tractor? So that can go and parse hundreds of pages of my manuals for my combine, my sprayer, my tractors. My specific tractor had a hydraulic line blow last Friday, and to find the place in that tractor for the information took a long time. So as you can see here, it tells us what we need to know. And it will even speak it out. This took me about 15 minutes to find in the 500-page manual for a tractor. I hope you enjoyed, and I also invite you out to our farm to see all the different projects that we're doing here with Microsoft, and really how AI can help us revitalize rural America. Thank you.
So yeah, so with that, I want to conclude the talk. You heard about different things in the context of agriculture, all the way from our vision being that of democratizing data-driven agriculture. We want to make sure that every farmer anywhere in the world is able to use data and AI, all the things you talked about. The first thing we built was the data platform, for which we need connectivity in the middle of the farm. We need edge compute. We need to do multimodal AI. But on top of it, the part that's gotten us really excited is, until now, we were getting all the data, generating insights, but with all the things I talked about with ChatGPT, you can actually turn those insights in a way that you can deliver it to the farmers anywhere in the world. So this is an active project. We are continuing to work with various partners around the world to light this up. And really looking forward that hopefully this would have sparked some ideas into the work that you all are doing. Thank you.
Any questions? Related to your talk itself. So you showed one part of the sensors and the connectivity, all the sensors collecting data, and then the use cases that you showed of AI didn't seem to use any of the data that you mentioned in the first part. So is this like there's some work that you did and you just including it, or are there separate pieces that you haven't connected?
Right. No, they are part of it. Like, for example, I talked about the use cases around, I'll show you these use cases, for example, all the, these use cases of Copilot that I talked about. These are all using data from the farm, from satellite data, all of that. So this is all, so it's all building. If you think of the entire stack, the lowest level is connectivity. You need to connect the farm. You need to get the data. But that is kind of invisible to the upper layers. Because once you've gotten the data from the farm and from other places like weather stations, satellites, we then merge all of this data. So what's coming up is a merged view of what's going on. So when you ask questions like what's happening in the farm and things like that, you don't really know how the data came. Because for us, you have to create that uniform view of a farm, that data representation of the farm. And that's the key, this thing that I talked about over here with this common data model. Everything is hidden behind here. All the connectivity, all the IoT pieces is hidden here. So that what you're seeing is on a daily basis, and we are running this thing of what is happening in the farm. So creating that farm context is critical. And behind that, you need connectivity in the farm, you need IoT sensors, all of that stuff to get there. Yeah. So it was kind of implicit, like, it's hidden. That's why as networking researchers, often we are seen as plumbers. We create that link, right? But that's invisible to the upper layers. Yeah. But if you break that, then everything else breaks. Yeah.
Talk about most of the things very interesting to learning. Just keen on knowing how in the robotics next generation,
Yeah,
after
yeah.
4 years, these robots are
Yeah,
doing potential at household level. So
yeah.
I think agriculture could be much more.
No, it is. Agriculture at multiple levels. I think robotics is playing a very important role, all the way from the starting point being drones, of course. Drones, when we talk of aerial robots, drones are first used for scouting. That is, I'll have a camera on a drone, it'll go and scout, it'll tell me what's happening where in the farm. But that's just a starting point. The next thing, which is actually getting deployed here, I'm the advisor of a company here, where what they're using is spraying drones. And the farmer I showed here in the end, Andrew, he uses it too. That is, these drones would go, and if I have to spray chemical in a farm, rather than driving your tractor, then spraying it, I'll just put a drone, drive in a pickup truck, take out my drone and spray where it is needed. That is something which is taking off as well. That's around, payload. The third piece around drones is drones carrying humans, but that'll be in the future. I'm not getting there. The other part where robotics is taking off is on ground robots. Like the number one stage, there is self-driving tractors. This you'll start seeing in the developed world a lot, like in Australia, in the US, where farmers, they operate a fleet of tractors. They're all self-driving. They just go figure out what's happening around. But that again, that needs AI, that needs connectivity. One of the key challenges, like I was talking to one of the big tractor companies in India, and they were talking about, for grapes, for example, they have to go beneath the orchard. A lot of times when you're applying chemicals, they don't want humans sitting in the tractors because it's dangerous. Can you just have an autonomous tractor that goes underneath the canopy and sprays the chemicals? So that's again one of the use cases of robots is around the self-driving tractors. People are also talking about these robotic harvesters. Like they will go and harvest not just grains. There's some work happening in Washington State University where there are these robots that are harvesting apples. They have like a hand which goes and grasps the apple and picks it. That's a challenging problem for robots because you don't want to grasp it too hard because it'll damage the crop. So there's a lot of work happening there. There's another company, I think it's called Carbon Robotics, again based out of the US, in the Seattle area. What they're doing is they're building these tractors with lasers at the back. So what these lasers do is wherever there is a weed, they'll just zap that weed with laser. So there's work happening on that too. This is all automated. You just go with a camera, it'll figure out it's a weed and just zap it. So that's again another use case of robotics. Another use case of robotics are small robots, small ground robots, where what people are building, this is a company, EarthSense, out of your University of Illinois. And what they're building are these ground robots with lots and lots of sensors on it, this tiny. It goes below the canopies and it takes images of your entire crop. This is very important for phenotyping. This is important for various other use cases as well. That you just leave it, it'll go, it'll scan your entire field and come back. So this entire space is taking off and taking off in a big way. It's interesting that, you would have thought that if people are doing self-driving cars, people would have built self-driving tractors before that. That hasn't kept pace, but it is catching up. I think it will happen. And finally, all the things with Gen AI and humanoid robots, I don't know. That's a totally different space and its impact in agriculture. If you have robots that look like humans, what they'll do in the middle of a farm, who knows? Maybe that is the future. You'll employ, instead of multiple farmers, you'll employ multiple humanoids and send them out to do something. It's bound to happen, something. But yeah, overall, robotics is a critical aspect, all the way from drones to ground robots to maybe in the future humanoids. Yeah. Yeah.
It's about reasoning chains.
Mhm.
The particular one that you showed seems to have a long chain of these, and it takes only one wrong direction or one incorrect step, and then it could be going. So, what kind of guardrails do you have? Checks that ensures that
This reasoning is doing a good job. Yeah, at this point, this is still early. Reasoning, especially for enterprise scenarios. So I've just taken a new role, by the way, within Microsoft, where I'm the general manager for one of our key enterprise copilot products, where we are looking at, one of the challenges we are looking at is how do you take these O1 reasoning models to those enterprise scenarios, where I'm asking it to take a decision to reason about something. A lot of guardrails is done when we are fine-tuning the model. Training the reasoning model itself is where we'll make sure that it's trained. There, the samples that we use to train the reasoning model, it's critical to have them of very high quality, right? So that's critical. The other piece that we add is a check, like once you're done with something, ask it to check the result. And that actually improves the accuracy significantly in many cases.
Have a logic that
Yeah.
does the check and says that.
So no, in this case, you can ask the same reasoning model to check the answer itself. So you give it the answer and ask it to check it. It's like, the way we do math questions, the way we teach kids to do math. They do the math and check it. So we do that, and that helps improve it. The third thing we're looking at is also using what you said, these static checkers and analyzers post the result to go and check whether the answer is correct or not and flag any anomalies in it. So that's another thing that we have to do. But that said, do we think we've solved it? No, it's still actively in progress, right? We never know when things could fail. O3 is even better. The other thing we've learned is that with test time compute, the longer you let it think, the more likelihood it is of getting a better answer. It's more expensive though. The longer you have it think, the more expensive it gets. But the likelihood of it generating a right answer is higher. So yeah, but these are all things that we are learning on the fly. This is such an active space of research. Yeah. 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 Thank you.
Some refreshments are served in this year.
Thank you. Hi. Oh, hi, Rajesh. Very nice to meet you. Yeah, thank you.